Hello everyone. Generating realistic human dance from music has seen incredible progress. But what if we want to tweak a specific move? For instance, telling the AI, instead of jogging, can you make the character do side steps, or now, can you make them kick their legs slightly? This is the challenge we address. We introduced DanceEditor, a novel framework for iterative and editable music-driven dance generation using open vocabulary descriptions. As you can see here, our framework first generates an initial dance based solely on the music, accomplishing the fundamental task of music-driven dance generation. If you're not satisfied with the generated dance movement at this point, we can provide a text prompt, such as convert jogging into behind side steps, and the model precisely edits the motion. If you're still not satisfied, we can take this edited result and refine it further with another prompt, like step forward and cross feet. This demonstrates the core strength of our work: high quality, multi-turn, and multimodal dance editing. So, how did we achieve this? Let's take a look at our DanceEditor framework. To achieve our goal, we propose an innovative prediction then editing paradigm. Our framework consists of two key branches. The generation branch, shown in blue, is a powerful diffusion-based model that generates high-quality initial dance sequences conditioned only on music. This forms the foundation of our system. The core of our innovation lies in the editing branch, shown in pink. Inspired by the control net architecture, we lock the weights of the pre-trained generation branch and introduce this new, trainable branch to handle the editing task. It takes multimodal conditions, the initial motion, the music, and the text prompt to guide the editing process. Within the editing branch, we designed a crucial component, the cross-modality editing module, or SEM. This module represents our core insight. The SEM is designed to effectively integrate the guidance from different modalities. It takes the features from the initial dance, the current motion, and the text prompt, and projects them into a shared space. Its key operation is to compute a dynamic fusion weight. This weight determines how to adaptively blend the rhythm from the initial dance with the evolving new motion, all under the precise guidance of the text prompt. This fused guidance is then injected into the main denoiser via an ADA in layer, allowing for fine-grained control without disrupting the motion's naturalness and musicality. This module is the key to achieving temporally coherent and semantically accurate dance editing. Of course, a powerful framework requires high-quality data. Since no existing dataset could support our task, we had to build one from the ground up. So, what is the Dance Remix dataset? We introduced Dance Remix, the first large-scale, multi-turn editable dance dataset. It is massive, comprising over 25 million motion frames and 84,000 dance pairs, with a total duration of over 117 hours. As this table shows, existing datasets lack the crucial edit prompt modality. To create our dataset, we developed a novel automated workflow. First, we use a retrieval model to find pairs of similar motions. Then, we align them to the same music beat. The most creative step is next. We use a powerful multimodal model, Gemini, to generate dense captions for the dance videos, and then leverage a large language model, GPT-4o, to synthesize the transformation script, or edit prompt, between the two motions. This pipeline allows us to build a rich and diverse dataset efficiently. Here are some examples from Dance Remix. As you can see, our dataset covers a wide variety of dance styles and complex movements, providing a solid foundation for training robust models. The fundamental unit of our dataset is the similar dance motion pair. On the left, you see a source motion, and on the right, a target motion that is similar but distinct. Our automated pipeline not only aligns them to the same music but also generates detailed captions for each. These captions then form the basis for creating the final edit prompt, which is displayed above the right side motion. So, with our new framework and dataset, how does DanceEditor perform against state-of-the-art methods? We first evaluate the initial prediction stage of our model. Here, we compare its music to dance generation capability against recent state-of-the-art methods. Quantitatively, our method achieves superior results in FID, beat alignment score, and diversity. Qualitatively, as you can see from these visualizations, our generated motions are more natural, expressive, and better synchronized with the music compared to other methods. This proves that our generation branch provides a very strong starting point for the subsequent editing. But the true power of DanceEditor lies in its iterative editing capability. Here, we demonstrate a two-step editing process. We start with the initial dance generated from music. Then, we apply the first edit prompt. The model successfully modifies the dance while maintaining its flow. Next, we take this result and apply a second, completely different prompt. Again, DanceEditor precisely follows the instruction. This clearly shows our model's ability to handle sequential, multi-turn edits, a capability previously unexplored. To validate our design, we conducted thorough ablation studies. As you can see, without the editing branch, the model cannot perform any edits. If we use the editing branch but remove our core chem module, the results are poor. The edits are inaccurate and often break the motion's coherence. Only our full DanceEditor framework produces results that are both rhythmically consistent and semantically aligned with the text prompt. This confirms that both the editing branch and our proposed chem are essential for high-quality dance editing. Finally, here are more examples showcasing the versatility of DanceEditor. On the left of each pair is the initial music-driven dance, and on the right is the result after applying a single text prompt. From changing arm movements to altering leg kicks, our method consistently produces diverse and plausible edits, all while preserving the original rhythm and flow. In conclusion, we introduced DanceEditor, a novel framework for iterative and editable dance generation, supported by our new large-scale dataset, Dance Remix. We believe this work paves the way for more controllable and practical applications in choreography and virtual avatar animation. Thank you for listening.